Okay, so new section 5.5, the least upper bound property. In this section, we are going to see a property of the real numbers which the rational numbers don't possess. And this is one of the things that distinguishes the two number systems. And it's also the reason we construct the real numbers in the first place. So it starts with this definition. Of an upper bound. Let E be any subset of the set of real numbers. A real number M is said to be an upper bound for E if x is less than or equal to M for all elements x in E. If this happens, then we say that M is an upper bound for E. So here is an example illustrating this. Say our E is this closed interval. Zero comma 1, which is a subset of the real numbers. Then you can see that 1 is an upper bound for E, because by the very definition of this closed interval, every element in E is less than or equal to 1. One is an upper bound for E because x is less than or equal to 1 for all x belonging to 0 comma 1. Of course, it's also true that x is greater than or equal to 0, but we don't need to see that. We only care about this inequality. It is also true that two is an upper bound for E because all the elements of E are also less than or equal to 2. And in fact, every real number greater than or equal to 1 is an upper bound for E. That is because if we have a real number y, say greater than or equal to 1, then for every element x in this, x is going to be less than or equal to 1, so x automatically is going to also be less than or equal to y, thus proving that y is an upper bound for E. However, (0.5) is not an upper bound for E. Because 0.5 is not greater than or equal to every element of E. This condition that x is less than or equal to m for all x, it is a part of the definition. So if this inequality is not true for some x in E, then we cannot say that m is an upper bound, as is the case with 0.5. For example, 0.7 belongs to this closed interval, and 0.7 is not less than or equal to 0.5 because it's greater than 0.5. So that prevents 0.5 from being an upper bound for this set. Merely being greater than or equal to some elements of 0, 1 is not necessarily enough for 0.5 to be an upper bound. It needs to be greater than or equal to every element, then only we can say it's an upper bound, which it is not. Then there is another example. Let R plus denote the set of all positive real numbers such that x is greater than 0 and ink. This set R plus has no upper bound Why is it that it has no upper bound? It's because let me just show it. I'm not going to make it a part of this example. Let me show it here why it does not have an upper bound. Suppose suppose this has an upper bound. Say there is a real number m such that x is less than or equal to m for all x belonging to R plus. Okay, then we already know that for any given real number there exists a positive integer by the Archimedean property n such that n is greater than m. If m itself is negative, but m cannot be negative because the elements in R plus are positive, and we have supposed here that x is less than or equal to, fine, so m is positive, so it's in fact better for us. So since m is positive, okay, so now we can argue like this: since m is positive as one belongs to R plus, and hence one is less than or equal to m, m plus 1 is also a positive real number. Thus, m plus 1 belongs to R plus. However, m plus 1 is not less than or equal to m. In fact, it's greater than m. So this supposition itself is contradicted. So that means the supposition has to be wrong, and that is why this set has no upper bound. So unlike the closed interval 0, 1 that we have here, this is a subset of R that has no upper bound. So this, I said I am not going to make it a part of the solution. We just consider it as something extra. However, there is one more thing in this solution, more precisely, which we can write within brackets. This subset has no upper bound in R. Of course, because by the very definition of an upper bound for a set when it exists is first of all a real number, and then it satisfies that inequality, that condition. So R plus has no upper bound in R, but in section 6.2 we shall define the extended real number system which will allow us to have the upper bound plus infinity for R plus, which is something that we will see in that section only. That means to the system of real numbers we are going to add two extra symbols, plus infinity and minus infinity. That will give us a larger system, the extended real number system. In that system this set will have an upper bound plus infinity, which we will see what it means when we introduce this thing in section 6.2. Right now in the system of real numbers, with our ordinary definition of an upper bound, R plus has no upper bound. Example. One extreme case is when the set E is the empty set. The empty set has every real number as its upper bound. Because you see, if x is any real number, or okay, so let's just consider m itself. Let's keep the thing consistent. If m is any real number, then the statement that x is less than or equal to m for all x belonging to E is vacuously true. It's because you see, this statement can also be written like this: if x belongs to E, then x is less than or equal to m. So it's an implication whose hypothesis is false, so the implication is vacuously true. So in this case only, this is the only set where every real number is an upper bound. Okay, now it is clear that if m is an upper bound for the subset E of R, which is some subset, then any real number greater than or equal to m is also an upper bound. which we have seen in the first example itself. 1 is an upper bound for the closed interval 0, 1, and so is every number greater than or equal to 1. However, what is not clear is whether E has any upper bound less than n. It may or may not have such a thing, or less than m, sorry. If we have one upper bound m, then the larger numbers are automatically upper bounds, but we may or may not be able to find a smaller upper bound than m, and this prompts the next definition, which is very important. Where we see the notion of a least upper bound. Let E be a subset of R. A real number m is said to be a least upper bound for E if there are two conditions that need to be satisfied. If A, m is first of all an upper bound for E, and condition B, if S is any upper bound for E, then m is less than or equal to S. So that means a real number m is a least upper bound for E if m is an upper bound for E and m is the smallest among all the upper bounds. That's why it's called a least upper bound. Now, merely defining this is not enough. I mean, what I'm trying to say is that if we are given a set E of a subset E of the system of real numbers and say it has an upper bound, does it automatically imply that it will have a least upper bound? The definition doesn't say anything about that. The definition merely says that if there is one such smallest upper bound, then that is a least upper bound. It may or may not exist. The magical thing about the system of real numbers is that if E is non-empty and there is at least one upper bound, then there must be a smallest upper bound. And this is the least upper bound property, which sets it apart from the system of rational numbers, which lacks this property. So that's what we are going to see. That is the main thing in this section. But before we see that, let's just see some examples, and there is one result also which says that whenever a least upper bound of a set exists, then it must be unique. There is only one least upper bound when it exists. So let's first see one example illustrating this definition. Let again E be the closed interval 0, 1. Then as we have seen before, one is an upper bound for E, which we already know. However, more is true. One is not just any upper bound for E, but one is a least upper bound. It is the smallest among all the upper bounds. Indeed, any number greater than or equal to 1 is an upper bound for E, but only 1 is the least upper bound. The other upper bounds are all strictly greater than 1. We are simply mentioning this, or we are just stating this without a proof, but a proof can easily be given. There is no need to show that 1 is an upper bound. That follows directly from the definition of E. I mean, from the definition of this particular closed interval. However, to show that 1 is the only least upper bound, or in fact 1 is a least upper bound, that comes first. No? So you assume Y to be any upper bound for E. Then that implies that X must be less than or equal to Y for all X belonging to E. In particular, you can take X equal to 1 because 1 is also an element of E. So that gives you 1 less than or equal to Y. So this shows that whenever you have any upper bound Y for OB, we cannot claim that Y is in E. Y is in R and Y is an upper bound for E. If that is the case, then it must be that 1 is less than or equal to Y, and hence 1 is a least upper bound. And in fact, if one argues a little more, one can clearly see that 1 is the only least upper bound. There can be no other, which in general is also true. A set, whenever it has a least upper bound, the least upper bound is unique. That is something we are going to show soon. Then there is one other example. The empty set has no least upper bound. Why, you ask? The argument goes like this. Again, say M is a least upper bound for the empty set. Then, since we have already seen before that the empty set has every real number as its upper bound, so in particular M minus 1 will also be an upper bound for the empty set. However, M minus 1 is strictly less than M. So this violates condition B of this definition, that M is a least upper bound. So since M is a least upper bound and M minus 1 is an upper bound for the empty set, we should have M less than or equal to M minus 1. But at the same time, we have this. So trichotomy is violated. So that's why the original supposition is wrong, that is, the empty set cannot have a least upper bound. Note, however, that it has upper bounds, and in fact every real number is an upper bound for the empty set. This is an extreme case, but nonetheless it's the case. Okay, now we come to the proposition which says that a set can have at most one least upper bound. Proposition 558. Uniqueness of least upper bound. Let E be a subset of R, then E can have at most one least upper bound. The proof is quite easy. We will assume that there are two least upper bounds, and we will argue that they in fact have to be equal. Let M1 and M2 two real numbers be least upper bounds for E. Since M1 is a least upper bound and M2 is an upper bound, because you see M2 also is a least upper bound, but that implies by the very definition of a least upper bound that M2 first of all is an upper bound. Now you combine these two things, M1 is a least upper bound and M2 is an upper bound. Now you apply part B to M1, then M1 must be less than or equal to M2. M1 is smaller or equal to every upper bound. In particular, M1 is less than or equal to M2. Similarly, since M2 is a least upper bound, and M1 is an upper bound, we must have this. So we can now combine these two inequalities and apply the fact that this relation is anti-symmetric. That means M1 must be equal to M2. Thus, M1 is equal to M2. Hence, E can have at most one least upper bound. So this excuse me, ends the proof. Note that in the proof we are not using any, we are not supposing that E in fact has any upper bound at all. All we are doing is that if there are two upper bounds, two least upper bounds for E, then they must be equal. That's what we have shown. So this whole thing is itself an implication, a conditional statement that if there are two least upper bounds, then they must be equal. There may not be any least upper bound for E at all. In fact, there may not be any upper bound for E at all. Just like R plus. R plus, that's the set of all positive real numbers. We have already seen that it has no upper bound. What is this proof for this particular set? If you take E equal to R plus, then this proof says that if M1 and M2 are two least upper bounds for this E, then M1 is equal to M2. So in this implication, the hypothesis is false because R plus has no upper bound to begin with. So how can it have any least upper bound? So because the hypothesis is false, the implication in this case is vacuously true. In fact, this is the case with most such implications. If the hypothesis is false, then there is no need to worry about the situation because the implication will be vacuously true. Only when the hypothesis is true do we have to actually show that the conclusion is also true. So whenever a least upper bound exists, it must be unique. That much we have shown. Okay. Now comes the hard part. The next thing we are going to show is that if we take a non-empty subset of the real numbers which has at least one upper bound, then it must also have a least upper bound. So this was the uniqueness of least upper bound. Now we are going to prove existence of least upper bound. Let E be a non-empty subset of R. Keep in mind that we have already seen that the empty set has all real numbers as its upper bound. So naturally it has no least upper bound. However, if our set is non-empty and has an upper bound, then it must be it must have a least upper bound. If E has an upper bound, that is, if E has some upper bound, then E has a least upper bound. The proof of this theorem is not easy, but let's see how we can prove it. Actually the theorem not only says about the existence of a least upper bound, it in fact says that there is a unique least upper bound. So although it's named like existence of least upper bound, but the uniqueness has also been made a part of this, has exactly one least upper bound. So that exactly one part we can argue from this result, this proposition, by proposition 558. E has at most one upper bound, at most one least upper bound. We shall now show that E has at least one least upper bound. Okay, since E is non-empty, we can choose an element x not belonging to E, some element. let M be an upper bound for E. Okay, so this is one thing. Non-emptiness of E has allowed us to choose one element x naught in E. Besides that, the other thing is that since E is bounded, or I should not say bounded above, since E has an upper bound, so we can choose M to be an upper bound for E. There is some upper bound. Now let N be any positive integer. By the Archimedean property, which was specifically, what is the, just give me a moment, it was corollary 5,4,13. So by the Archimedean property, there exists a positive integer n or k, whatever we want we can take. They have taken k. Okay, such that k divided by n is greater than or equal to m. Okay, yes, because n is a positive integer, so 1 divided by n is a positive real number and m is any real number. So you can find a positive integer k such that if you multiply 1 over n by k, this product is going to be greater than or equal to m. In fact, actually strictly greater than m, but same. I mean, if you have strict inequality, you can write greater than or equal to also. So now note that since m is an upper bound for E, so all the elements of E are going to be less than or equal to m. And because of this inequality, all the elements of E are also going to be less than or equal to k by n. In other words, k by n is also an upper bound for E. Is also an upper bound for E. Again, the Archimedean property gives us a positive integer L prime say, such that L prime divided by n is greater than minus x naught, because x naught is an element of E. So minus x naught is a real number and 1 divided by n is a positive real number. So we will also have, by the Archimedean property, a positive integer L prime such that this inequality is true. Multiplying 1 over n by L prime gives us a real number that is greater than minus x naught. Then L divided by n is going to be less than x naught, where L is minus of L prime. Note that because L is the negative of L prime, which is a positive integer, so L is again an integer, although it's negative but it's still an integer. Okay, so now you see that this real number L divided by n cannot be an upper bound for E, because one element x naught of E has exceeded this real number. X naught is not less than or equal to L by n. X naught is in fact greater than L by n. So L by n fails to be greater than or equal to every element of E, and that's why L by n in particular cannot be an upper bound for E. Since x naught belongs to E, we see that L divided by n is not an upper bound for E. Okay. Now L divided by n is less than x naught, which must be less than or equal to k divided by n, because k by n is an upper bound for E. K divided by n implies L must be strictly less than k. The integer L must be less than the integer k. Okay, now in the next paragraph, so let us just see what we have got. N was chosen to be any positive integer. For such a choice, we have found that we can find integers k and L which are related to each other like this, and such that L by n is not an upper bound for E, but k by n is an upper bound for E. So from these two things we can find a sort of boundary of these two integers. In that boundary, what will happen is that on one side of the boundary we will find an integer such that that integer divided by n will not be an upper bound for E. But if you increase that integer by 1, then that divided by n will be an upper bound for E. Specifically, we mean this: since k by n is an upper bound for E and L by n is not an upper bound for E, there exists an integer mn such that mn is strictly greater than L, mn is less than or equal to k, mn divided by n is an upper bound for E, and mn minus 1 divided by n is not an upper bound for E. So this mn minus 1, this is an integer that is at the boundary of these two things. This ratio is not, this quotient is not an upper bound for E, but if you increase this mn minus 1 by 1, then you get the quotient mn by n, that is an upper bound for E. And this mn lies between the integers L and k in this manner. However, simply saying that we can find such an mn is not enough, we have to actually prove it. That, however, will be done in one of the exercises at the end of this section. See the second exercise. In fact, not just that this mn exists, but it is in fact unique. And that is shown in the third exercise. Okay, so we leave showing these things to the exercises so that we can concentrate on the main matter. We subscript mn, the integer mn by n. You see that the integer mn has a subscript n. This emphasizes the fact that mn depends on n. Keep in mind that all these things are happening for every positive integer n. So you choose n equal to 1, for that there is one such m1. You choose n equal to 2, there is m2, and that integer is unique. If I choose an n, then mn exists and is unique, which has these properties, that mn minus 1 by n is not an upper bound for E, but mn by n is an upper bound for E. So we subscript mn by n to emphasize the fact that mn depends on the choice of n. Okay, so we have a well-defined and unique sequence m1, m2, m3, etc. of integers for which these things happen. with each mn divided by n being an upper bound for E and none of the numbers mn minus 1 divided by n being an upper bound for E. Okay. Now the next thing we want to show is that this mn by n, it changes as n changes. In particular, this is a sequence and you can see that each such number is a quotient of two integers. So each mn by n is a rational number. So this is a sequence of rational numbers. We now next want to show that it's a Cauchy sequence of rational numbers so that we can find its formal limit. Okay, so let me just put some ink first. Now let capital N be any positive integer and n prime be integers satisfying these inequalities, that both n and n prime are greater than or equal to n. Since mn divided by n is an upper bound for E and mn prime minus 1 divided by n prime is not an upper bound for E. We have mn prime minus 1 divided by n prime less than mn divided by n. How are we concluding this inequality? You see, since this is not an upper bound for E, so there will be some element in E, say y, that will be strictly greater than this number, because if this number becomes greater than or equal to every element of E, then it becomes an upper bound for E. So this not being an upper bound means there will be at least one element in E which is not less than or equal to this number, that means which is greater than this number. But at the same time mn by n is also an upper bound for E, so this element of E must be less than or equal to mn by n. So that's how we are getting this inequality. Okay. Now, from this inequality, we can say something. This implies minus 1 over n. Okay, we can in fact write the whole thing here itself. You will understand this is less than or equal to minus 1 over n prime, which is less than mn divided by n minus mn prime divided by n prime. The second inequality is clear. We have loosely speaking taken mn prime by n prime on that side, writing this. On the left hand side, we are left with minus 1 over n prime, and from this inequality, first of all, we have, since both n prime and n are positive integers, so taking reciprocals, we get this. Then if you take minus, if you multiply by minus 1, you will get this. That's what we have written here. Okay. Similarly, since mn prime divided by n prime is an upper bound for E, and mn minus 1 divided by n is not an upper bound, for E, so we have mn minus 1 by n less than mn prime by n prime, and hence, okay, in this case, we bring this one to this side, mn prime divided by n prime, and this will be less than, and we bring minus 1 by n to that side, and n is, since n is greater than or equal to 1 by n, n, capital N, so 1 over n will be less than or equal to 1 over capital N. We thus have minus 1 over n is less than mn by n minus mn prime by n prime, which is less than 1 over n. That is, the absolute value of mn by n minus mn prime by n prime is less than 1 over n, where, or in fact it will be better we write like this: for all integers n and n prime greater than or equal to n, True, here n and n prime, once we have chosen them, they are fixed. But keep in mind that we chose n and n prime after choosing n, and this n is any positive integer. After that choice has been made, n and n prime also have been chosen to be any integer greater than or equal to n. So for a fixed capital N, you can in fact vary this n and n prime. You can choose them to be any integer whatsoever, but both of them greater than or equal to n. For such choices, this inequality is always going to be true, and this implies the sequence mn divided by n is a Cauchy sequence. Also, each m of why is it a Cauchy sequence? That is also an exercise. This is the fourth exercise. There we will show, it's actually quite easy, but nevertheless we want a proof. Also, each mn by n is a rational number. So we now have got a Cauchy sequence of rational numbers. So it will have a formal limit. Let S be the formal limit of this Cauchy sequence. That means S is a real number associated to this Cauchy sequence. Since by exercise 548, no, not that one, exercise 535, we have this. If you go back to this exercise, there you will see we have proved that this formal limit is equal to 0. In other words, the Cauchy sequence 1 over n and the 0 Cauchy sequence are equivalent. So since we have this, so S also becomes equal to the formal limit of this sequence, which if you see, it is nothing but the difference of this formal limit, that is this real number S, and 0, where 0 is this limit. So if you take the difference, then by the definition of difference of two real numbers, inside you get mn by n minus 1 by n. So that gives you mn minus 1 divided by n. Okay. Now this real number S, we are going to show, is actually the least upper bound for E. That S is the least upper bound for E. so that requires two things. First, we have to show that S is an upper bound, and then that it is the smallest among all the upper bounds. So let X belonging to E be any element since Mn divided by n is an upper bound for each positive integer n, we have x less than or equal to Mn by n for all n greater than or equal to n. So here we have in fact infinitely many upper bounds, one for each positive integer n. We have used that thing with the particular element x, which actually is any element of E. So for that we get these inequalities. Now by exercise, so the exercises are being used very nicely, I mean the ones we have already solved previously. So by exercise 548, x will also be less than or equal to the formal limit of this sequence, which is nothing but S. So we see that S is greater than or equal to any element x of E. So that proves that S is an upper bound for E. Next, we will show that S is a least upper bound. So for that, let T be any upper bound for E, since Mn minus 1 divided by n is not an upper bound for E for all positive integers n. We have Mn minus 1 by n. If it becomes greater than or equal to T, then on account of the fact that T is an upper bound for E, we would then have to conclude that this is also an upper bound for E, which it is not. So that's why this cannot be greater than or equal to T, it has to be less than T. But then by exercise 548 again, the formal limit of this sequence Mn minus 1 divided by n must be less than or equal to Note carefully that according to this exercise, although we have strict inequality here, but once we take formal limit, all we can say is that it's less than or equal to t. We cannot claim that here also we have strict inequality, just like this thing. All the terms of this sequence are strictly greater than 0. But when we take formal limit, on the right hand side also we have 0, on the left hand side also we have 0, and 0 is not less than 0. So that's why we are writing less than or equal to t. That is, this is again that this limit is also equal to s. So s is less than or equal to t. So this shows that s is the smallest among all possible upper bounds. Hence, s is the least upper bound for E. So this completes the proof. Completes in the sense that of course we have gaps. We have to fill those gaps in the exercises. Now, having proved this thing, we are next going to define something which we will use again and again in real analysis, namely supremum. Let E be any subset of the set of real numbers. If E is non-empty and has some upper bound, then we define sup E to be the least upper bound for E, whose existence and uniqueness is guaranteed by the theorem we have proved just now. So by theorem 559, exists and is unique and hence is well defined. Okay, so this is when E is non-empty and has some upper bound. We introduce two new symbols. Minus infinity and plus infinity, which of course are just some abstract symbols as of now. If E is non-empty and has no upper bound, like that set of all positive real numbers. If E is like that, then we define supremum of E to be plus infinity. However, if E is empty, then we define supremum of E to be minus infinity. Right now, these are just some fancy ways of saying the same thing. This means that E is empty. This means that this one means that E is non-empty but has no upper bound. However, in the other possible case where E is non-empty as well as it has an upper bound, then by sup E we mean the least upper bound for E. So, as we have already remarked, when we define the extended real number system, there these symbols are actually elements. These are not just some abstract symbols. There we will have upper bound of a set equal to plus infinity that will take on a different meaning. For example, in the extended real number system, this has a meaning of its own. Okay, so with this I end this video. In the next part, we will see how one can use this least upper bound property to answer some of the questions, to address some of the issues that we came across in the system of rational numbers. For example, we have already seen that there is no rational number whose square is equal to 2. So, such types of numbers can now be produced. In the system of real numbers, there is in fact a positive real number whose square is equal to 2. So, we will see such things which makes the system of real numbers, it justifies our construction of the system of real numbers. So, with this I end this video. If you find anything doubtful here, please write in the comment section, and that will be all for real analysis today. So, see you in the next part. Until then, it's me, Lucifer, from A Mathematical Room. Have a nice night.